Today we're going to look at the quadratic formula and how it's derived. We start by looking at the most general form of a quadratic equation and setting it equal to naught to see where it crosses the x-axis, where the roots of the quadratic are, and then rearranging that formula to make x the subject and what we come up with. So, the most general form of a parabola is given by ax squared plus bx plus c, where a, b, and c are elements of R, though typically they're counting numbers. So for example, we have x squared minus 5x plus 4. So a has taken the value 1, b has taken the value minus 5, and c takes the value positive 4. And if we look to the right, we can see where this parabola what it looks like and where it intersects the x-axis. It can be noted that this parabola can be factorized easily into x minus 1 and x minus 4. So if we set that equal to 0, then it means one of those two factors is 0. So either x is 1 or x is equal to 4. And you can see that's where x crosses, that's where the parabola crosses the x-axis at 1 and at 4. Looking at this slide, we'll start with ax squared plus bx plus c equal to 0. So we set this general form equal to 0. The next step is to divide through by a. Now recall that a is not equal to 0. If it was, that general form would have reduced to just being a linear form, bx plus c. So we divide through by a. That gives the leading term a coefficient of 1. Becoming x squared plus b on ax plus c on a is equal to 0. The next step is we move the constant term over to the right-hand side. So it becomes now x squared plus b on ax is equal to minus c on a. And so the last step on this page is we now go about completing the square. Completing the square. Suppose we have x squared plus 3x. As we can see, that's not a fully completed expansion of a square. So the question is, how do we complete the square? Well, let's take a few examples and see if we can extract a pattern. In the case of x plus 1 squared, this expands to x squared, square the first term, plus 2x, plus or minus twice the product, plus 1, square the second term. In the case of x plus 2 squared, this expands to x squared plus 4x plus 4. In the case of x plus 3 squared, this expands to x squared plus 6x plus 9. In the case of x plus 4 squared, this expands to x squared plus 8x plus 16. And lastly, for x plus 5, we get x squared plus 10x plus 25. So what we can see when we look at this is the middle term, that is the x term, has a coefficient which is twice the second term in the brackets. So if we look at the first line, x plus 1, the coefficient of x when x plus 1 squared is expanded becomes 2. If, for example, we look at the third line, x plus 3 squared, that leads to an expansion where the coefficient of x is 6, or twice 3. And if we look at the last line, for example, x plus 5 squared, that expands to x squared plus x squared plus 10x plus 25. So the 5 is doubled. So the coefficient of the x is double the second term in the brackets. And if we look at the last term, that just appears to be the square of the second term in the brackets. So if we look at the first line, x plus 1 squared is 1. If we look at the second line, x plus 2 squared is 4. If we look at the third line, x plus 3 squared is 9, and so on for 4 and for 5. So when we get back to x squared plus 3x, if we're going to factorize it, we need to now look at how we reconstitute the coefficient of the x, which will probably be half of the 3, given what we can see below. So when we expand, that second term in the brackets doubles for the coefficient of x. So the coefficient of x, if we halve it, we'll get the second term in the brackets. Completing the square. So more generally, x plus a squared expands to x squared plus 2ax plus a squared. Let's have a look at y. So x plus a squared means x plus a times x plus a. So how do we multiply that out? First of all, the rule, or the acronym is FOIL, F-O-I-L. F means the first two terms. X times x, that gives us the leading term of the expansion, x squared. O means the outer two terms, x of the first bracket and a of the second bracket, that gives us ax. I means inner two terms, so a of the first bracket and x of the second bracket, that gives us ax. So ax plus ax is 2ax, that gives us the middle term of the expansion. And L of FOIL means the last two terms, a times a is a squared, and that gives us the final term of the expansion. So, to get x squared plus 3x, if we equate that with what's above, if we know that the coefficient of the x, when we expand x plus a squared, is 2a. So if we set 2a to be equal to 3, then that means a must be equal to 3 on 2. So in the bracket, we have x plus 3 on 2. And then to get the final term, we know that we square that second term. So we go 3 on 2 squared and we get 9 on 4. Hence we have our expansion and we've completed the square. Going back to what we had before, after that explanation on completing the square, we had ax squared plus bx plus c equals 0, setting equal to 0. The next line was dividing through by a being non-zero, giving us the quadratic. That is x squared plus b on ax plus c on a equals 0. The next line was moving that constant term over to the right-hand side and then completing the square. So we had x squared plus b on ax, which we needed to complete the square of, is equal to minus c on a. Now, having looked at that tutorial on the previous slide, we know how to complete the square. X squared plus b on a x plus b squared on 4a squared. So what we did was we halved the coefficient of the x. B on a halved is b on 2a, then we squared it. B squared on 4a squared. And so because we've added that to the left-hand side, we add it to the right-hand side. Okay, so we were up to x squared plus b on ax plus b squared on 4a squared. So we had completed the square, and that was equal to b squared on 4a squared minus c on a. Now for the next step, we're going to collect the terms. So if you look on the right-hand side, we can find a common denominator. And this is what we talked about in our fractions video. The common denominator for 4a squared and a is obviously 4a squared, because a divides into 4a squared. How many times does a go into 4 times a times a? 4a. So the numerator is scaled up by a factor of 4a. So we end up with b squared minus 4ac all over 4a squared. So for the third line, we now realize that we can factor the left-hand side because we have completed the square. So we can write that as x plus b on 2a. Recall that the coefficient of the x on expansion is double the second term. So that means the second term must be half of the x coefficient. Half of b on a, half of b on a is b on 2a. So we have x plus b on 2a squared is equal to the same right-hand side as above, b squared minus 4ac on 4a squared. And then for the last line, we take the square root of both sides. So x plus b on 2a is equal to plus minus the root of b squared minus 4ac all over 4a squared, which needs to have its square root taken as well. We're almost there. What we had at the bottom line of the last slide was x plus b on 2a is equal to plus minus root of everything under the root sign, b squared minus 4ac over 4a squared. Now, we bring that term on the left-hand side over to the right-hand side, and then we will have made x the subject completely. So, if we're adding on the left-hand side a term, in order to get rid of it, we subtract. And so we subtract on the other side. So x is equal to minus b on 2a plus minus root of everything as I mentioned before. Now, it should be noted that the denominator of that fractional quantity under the root sign is 4a squared. And if we take the root of that, we get 2a. So we can remove the root sign from over the whole quantity and just keep it over the numerator and rewrite the denominator as 2a, which matches the first term. So we get minus b plus minus root b squared minus 4ac all over 2a. And that is the quadratic formula. As always, it's useful to use examples to demonstrate how something works. So let's have a look at this one. Example 1, y equals x squared minus x minus 6. In this case, our coefficients are 1, minus 1, and minus 6. That is, the coefficient of the x squared term is 1, the coefficient of the x term is minus 1, and the constant is minus 6. We happen to know that this can be factored as x minus 3 multiplied by x plus 2. And so if we set that equal to 0 to see where it crosses the x-axis, either the first factor is 0, x minus 3, yielding a value of 3, or the second factor is 0, x plus 2 is 0, yielding a value of x equals minus 2. So as you can see by the screen capture there, it cuts at x equals 3 and x equals minus 2. But if we plug that into the quadratic formula that we just derived on the previous slide, we get, lo and behold, x is equal to 3 and minus 2. Looking at a second example, y is equal to x squared plus 4x minus 1. The coefficients are 1, 4, and minus 1. The coefficient of the x squared term is 1, the coefficient of the x term is 4, and the constant is minus 1. In this case, this doesn't factorize into integer values. And as we can see from the screenshot, it cuts the x-axis somewhere just beyond or just lower than minus 4, to the left of minus 4, and somewhere just to the right of 0. So this is a case where we will need the quadratic formula rather than just being able to identify by inspection that it can be factorized. And in this case, when we plug this in, we will get the following values. X is equal to minus 2 plus root 5 and minus 2 minus root 5. This is a prime example of the use of the quadratic formula where something cannot be factorized. As always, thank you for watching. I hope this has been useful. The whole purpose is to help people and to make things clearly understandable. So if you enjoyed this, give it a like, and please feel free to subscribe as I'll be producing more videos regularly. Thank you very much.